Okay, hello there everyone. Welcome back for the second talk of our afternoon session. And it's a pleasure to have Gábor Tardos, and he's going to tell us about extremal theory of vertex and edge ordered graphs.
I would like to use this survey talk to advertise an area that's very close to my heart, and it's also full of results, but also full of open problems. So maybe you can work out some of them. So going back to the origins, classical extremal graph theory or Turán-type extremal graph theory is basically this problem. You have a forbidden subgraph, call that H, and then you are looking for a graph on n vertices, a simple graph, has at most n choose two edges, of course. Is it better now? Okay. So, again, Turán-type extremal graph theory deals with the following question. You have a H, that's the forbidden graph, and then you are looking for a simple graph on a given number of vertices that avoids that graph, meaning that there is no subgraph isomorphic to H in your graph, and you want to maximize the number of edges. So that's maximum number is denoted here by x, n, and h. And I don't have to tell you that this has also both a long history and that was very useful in many other areas of combinatorics. It has lots of applications. The earliest examples are a result of Mantel from 1903 about triangle-free graphs and the maximum number of edges of a triangle-free graph. And next one is from Erdős, from a cycle of length 4 was forbidden, and he gave bounds on how many edges a graph without a cycle of 4 can have, and use that in a number theoretic problem. And the name Turán-type extremal graph theory comes from Turán's theorem, which gives an exact bound, exact value for this x and h function for any clique. So that's a generalization of Montel's result on triangles. Most general result in Turán-type extremal graph theory is the Erdős-Stone-Simonovic theorem that gives this formula from the extremal function for any graph. And for the formula, you only need to know the chromatic number of the forbidden graph. So it's important that it identifies the chromatic number as the most important property of the forbidden graph. And also it gives this formula that is very often asymptotic formula for the extremal function, except in the case when this chromatic number is 2, then what you have here is 0 times n squared over 2 plus little of n squared. So the error term becomes bigger than the main term, and you only get that you don't have a quadratic number of edges if your forbidden graph is bipartite, but you don't have an asymptotic formula. So the most important open problems here are with bipartite graph, and there are lots of open problems here. I will mention, so some of them will come up during the talk, but this is just the background. So one more observation here in the last line. You can forbid more than one graph, and if you do that, then the same formula kind of applies, but with the smallest chromatic number among your forbidden graphs. So basically, if you do not forbid bipartite graphs, then forbidding more than one graph is asymptotically as the same as the forbidding just one of them, the one that has the smallest chromatic number. Okay, so what I really want to speak about is are extensions of this theory, and this particular extension is for vertex-ordered graphs. I will call them ordered graphs. So the vertices are ordered left to right, and this is an example of such a graph. And if you take a subgraph of it, like the red subgraph, then it naturally inherits the ordering. So still vertices are ordered left to right. And you can ask when this does not show up as a subgraph. So what is this? This is a path of length 5, or actually length 4, but with a particular vertex order. So instead of saying that you are looking for the most edges in a graph that does not have any path of length 4, you say that, okay, I just forbid this particular ordering of the path, and maybe you can add more edges. Maybe the extremal function is higher. It cannot be lower, obviously. If you don't have any path of length 4, then you don't have this particular one either. So let's start with a couple of examples. No? So let's have the definition here in writing. So I will denote ordered graphs with age with a subscript of less than, which represents the fact that it's an ordered graph. And you are looking for the same actual maximum number of edges in an n-vertex graph, simple graph again, but now it's an ordered graph, such that this particular ordered graph does not show up as a subgraph. So basically, you forbid subgraphs, but you forbid subgraphs with particular ordering. And now comes this list of examples, just to have a feel of it. So these are paths of length 3, all of them, but with different ordering. These are not all the ordering, but for each one of them, you can ask, what if this particular ordering is forbidden? So this is the most natural ordering. Vertices come left to right, as in the past, and these 3 are different kind of orderings. And for each of them, you can ask the extremal question, or you can forbid all possible ordering. There are, of course, more than 4, so these are just examples. But if you do forbid all possible orderings, so imagine that I draw here all these examples and more, I mean all possible orderings of the 4 vertex paths, then you get back the, oops, sorry, I wanted to show, bring your attention to this part here, then you get back the Turán-type extremal number for the path of length 3, and we know what that is. So we get back the classical question, but if you forbid just one of them or a few of them, but not all of them, then you get new questions. And so these are the results for these particular examples. This particular path of length 3 behaves like a click. It behaves exactly like the click. The extremal function is the same. This particular thing behaves like a click of size 3, well, with a small error term. And we know the extremal functions for clicks from Turán's theorem. This particular ordering behaves like a single edge. So this is an ordered graph with just a single edge. And it basically tells you that every edge of your graph has to be using the first or the last vertex. No other edge is allowed, so it's very easy to see that the extremal function is 2n minus 3. And maybe the most interesting is this last one, where you get the extremal function of n log n with a linear error term. Why is this the most interesting? Because this is a kind of extremal function that you never get with the classical theory. There is a very simple and easy to prove dichotomy in the classical theory. If your forbidden graph is a forest or tree or any cycle-free graph, then the extremal function is linear. But as soon as you have a cycle, then the extremal function of the cycle is a power of n, where the exponent is bigger than 1. So you never get a function that's in this gap. It's bigger than linear, but it's not a power of n bigger than 1. So this slide is about related results. Mostly related results that I will not speak about, but it's good that you hear about them. So this first bunch of results is something that really started this research. It's the extremal theory of 0-1 matrices, and you can also think about it as extremal theory of ordered bipartite matrix, bipartite graphs. It's a bipartite graph with a given bipartition, and you order the two parts separately. And the way they formulated it is the adjacency matrix of that graph. And basically the same questions were asked. There is a paper from Füredi, Bienstock, and Gyuri, and this particular paper I will mention a lot because they have very nice conjectures that some of them are still open, some of them have been resolved. Okay, another direction is extremal theory of convex geometric graph. And that corresponds to, instead of a linear order on the vertices, they consider a cyclic order on the vertices. So they consider this graph to be drawn in a convex n-gon. So an n-vertex graph will be drawn in a convex n-gon, and that gives a structure. These questions that you can ask with this kind of convex geometric graphs is also a subset of the questions that you can ask for ordered graphs, because if you forbid any cyclic shift of a forbidden order, then you actually forbid, so you can get back as special cases this question. That's a very nice paper of Brass, Karoly, and Walter, and they have very nice results in specific small forbidden graphs. This is something that I really won't speak about at all, but it's also related. These are about ordered graphs, so the same ordered graphs. Now you have a vertex order, but the question they study is a Ramsey theoretic. Well, these two papers prove related results about that. These are very nice papers, but I won't have time to go into the results they prove. And one more word about the motivation. I personally think that these questions are very nice as mathematical questions go, and I'm happy to work on them, but it's good to mention applications. So if you look at this first paper, maximum number of unit distances in a convex n-gon, so Zoltán Füredi proved that that's at most constant times n log n. And the way that he proved it is with this extremal theory of 0-1 matrices. Since that, a lot of these geometric extremal problems, oh, by the way, that's not believed to be sharp, but that's the best upper bound still after 28 or many years. Anyway, these kind of applications for geometric problems tend to come up very often. If your graph is, the vertices correspond to points in some geometric space, especially if it's the plane, then very often a natural linear order is also present among those vertices, and then you can apply ordered graph extremal problems very successfully. Another application that I don't have in the slide is a paper of Reicher, Rödl, and Schlacht, work on the extremal theory of hypergraphs, but not ordered hypergraphs, just general hypergraphs. And in some cases, they reduce this problem to the graph case. The graph case is always simpler, but the graph case they reduce to is an ordered scenario. Okay, so let's go to the most general result on Turán-type extremal graph theory was the Erdős-Thon-Simonovich theorem, and that has a counterpart here. You just have to find the correct version of the chromatic number there. So this was the formula for the Turán-type version, and this is the same formula now. And it also works for many forbidden graphs where you have to apply the smallest chromatic number here. And the thing is that for that you have to use the interval chromatic number instead of the chromatic number of the underlying unordered graph. So the chromatic number is how many independent sets you need to cover the vertices, and the interval chromatic number is how many intervals, independent intervals you need. So it's a proper coloring of the graph where an extra restriction is that each color class have to be consecutive. And that's a simpler notion than the original. It turns out that, yeah. So it's, no, I don't think it's news to anybody that this is NP hard to compute. This is however easy. You can use a greedy algorithm. You just take the longest interval for the first color that is independent. You are done with the first color, then you take the next color to be the longest interval after that. That's independent, and that will work. Okay, again, this is satisfactory for interval chromatic number at least 3, and it's very weak for ordered bipartite graphs. So we are basically back to the setting of those first 3 papers that I showed where they consider the extremal theory of 0-1 matrices. Not exactly the same thing, because here we want to avoid a bipartite graph, but the host graph, the large graph that has many edges and avoids this, does not have to be bipartite, but it's just a minor tweak to that question. So all those questions they asked is relevant in this theory also. So let's take an ordered bipartite graph. So it has 2 intervals, the left vertices and the right vertices. All edges are between the left vertices and the right vertices. And trivial observation is that the extremal function is, well, at least as big as the extremal function of the unordered version of the same graph. Obviously, because if you avoid all ordering of this graph, then then this specific ordering is also avoided. And the first conjecture that I mentioned from the Füredi-Hajnal paper is that they conjecture that mostly it's the same, well, not exactly the same, but maybe there is not much difference between these 2 functions, and this is the conjecture, and it happens to be false. So this is a result of János Pach and myself, that this particular ordered cycle has an extremal function that is at least n to the 4th third, and you don't have to count the number of vertices because this applies to every cycle of this type. So I guess you can figure out how to make smaller or larger cycles of this type. So it's basically a spiral, and then there is one edge that finishes the cycle. And I was told that every talk has to have a proof, so this won't be a real proof, but I give the construction. So the construction is such that the same construction avoids all of these cycles simultaneously. And it has constant times n to the 4th third edges. And here how it's work. You take n half points and then half rich lines, and the edge will represent an incidence between a point and line, so you connect them if the point is on the line. From the Meredith-Trotter theorem, you know that there are n to the 4/3 possible edges at most, but you also know that the Meredith-Trotter theorem is actually tight. So there are examples, and not very hard examples, like you can take a square grid as the set of points and the rich lines on the square grid, where this is actually achieved. So you can have a graph with n to the 4/3 edges. Now, that graph will have long cycles like this, a lot of them. So everything depends on the ordering. If you order them right, then this particular ordered cycle will not show up. And this is how to order them. You order the points left to right. So you specify a vertical direction, and relative to that, you order points left to right. It doesn't matter what you do with ties. And the lines are ordered by slope. Again, it doesn't matter how you break ties. And that's so that's the construction. And to make this into a full proof, you just have to check that this particular graph doesn't have any cycle of this type. And it's a very easy exercise. Okay, so how far? Okay, so the Furedi-Hajnal conjecture, this particular one was not true. So how far can be these two extremal functions from each other? And in this particular case, we proved that the difference is n to the, so the fraction is n to the almost 1/3. Where, well, construction gives 4/3, and if you want to avoid the long cycle, then, well, you can do it with more than n edges with an exponent, but the exponent will be very close to 1. And this is the best ratio that we know. There is no graph where actually 1/3 is achieved, but as far as I know, it can be as high as n to the 1 minus epsilon. So that's a nice open question. How can you find examples where this ratio is even bigger than here? Obviously, it cannot be bigger than n, because all of these functions are between n and n squared. So they formulated the same conjecture specifically for forest. So if you have a forest, then the Turán-type extremal number is just linear. I mentioned that for cycle-free graphs, you always have a linear extremal function for the classical theory. And maybe that's true for ordered bipartite forests. Too, that's open. That's my favorite open question in this whole area. I really would like to have a solution to this. But what do you really mean by almost linear? So it won't be exactly linear. So you can ask for maybe little of n to the 1 plus epsilon for any positive epsilon, or you can ask for just a polylog, so n times a polylog. Is that enough? Or maybe just n times log n. N times log n is needed because even in one of my first examples of a path of length 3, you got n times log n, so you get at least that much. So if any of these three is true, it characterizes the cycle-free bipartite, ordered bipartite graphs, because you see, if it's not ordered bipartite, then the Erdős-Stone-Simonovic theorem, or the ordered version of that, says that you have quadratic number of edges in a, so the extremal function is at least is quadratic, and if it's not forest, then well, then even the unordered version can be avoided by more than n to the 1 plus epsilon edges. So this is the state of the art. These two are open, and this very strong one, where you wanted to have n log n, is actually false. And it's false because Seth Petty gave an example where the extremal function of a given, that was actually an ordered bipartite tree on 10 vertices, if I'm right, maybe 11. The extremal function was more than n log n. It was n log n log log n, and later it was improved on by Park and Chi, and they constructed other bipartite forest where the extremal function is at least n times log n times log log n times log 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 n, and you can add more logs. But this is very weak. Not just n times polylog n is open, n times log squared n is also possible as an upper bound. On the positive side, with János Pach, we just try to prove the conjecture for, well, we try to prove it for all ordered bipartite forests, but the techniques we managed to obtain was good enough for all graphs at most 6 vertices, and we proved n times polylog n upper bounds for all of them. But there were 2 particular 7 vertex graphs where we failed. And the more recent result of Korandi, Tomon, and Weidert, or joint with Korandi, Tomon, and Weidert, is a bit weaker in that it just proves the weakest version, little of n to the 1 plus epsilon, but it's for a larger class of bipartite forests that I call degenerate, and that's the state of the art. So I won't give you the details of the proof, but I want to give you just what degenerate means, or what graphs this applies to. It's easier to explain with the adjacency matrix. So this is the ordered bipartite graphs on 7 vertices. This was one of the 2 that our methods with János Pach didn't apply to. And so you make a 3×4 adjacency matrix out of it. And now this is a degenerate because you can cut it horizontally such that there is just one column that has a 1 both above and below the line. So this is a legal cut. And if you cut it here, then you get 2 smaller adjacency matrices. One is just a line, just 1 row, that's okay. And the other can be cut again. So if you repeated cuts, you can split a graph, adjacency matrix, into rows, then I call it degenerate. And for these graphs, we proved an upper bound for the extremal function. And just a few words on the proof. It's a density increment argument, meaning that you start with a graph that has enough edges that you think that, well, they should actually contain this as a subgraph, and then you try to actually build this graph as a subgraph, and then you do this, you do that, and then you might get stuck. But if you get stuck, that means that you somewhere found a denser subgraph. So it's a density increment argument. So you start over with the subgraph that's already denser. It should also contain this as a subgraph. Well, either you succeed or you find an even smaller subgraph which is even denser, and eventually the density will be more than 1, and that's a contradiction. And this is the bound that we actually prove. It's a little bit better than, well, okay, so it's n times this. So it's not n times polylog n, but n times 2 to the log to the c of n, where c is less than 1. It's certainly n to the little of n to the 1 plus epsilon. And this is the, as I said, this is the state of the art. As far as I know, there is not a single bipartite ordered forest for which little of n to the 1 plus epsilon is proved for the extremal function, and it's not degenerate, except for the triviality that you can reverse the order here, and if you reverse the order, that is like taking the transpose of this matrix, and some matrices are degenerate in the transpose, of course, then the same bound applies, but other than that, we don't know anything, and this is the smallest example. So this is the adjacency matrix of 8 vertex-ordered bipartite tree, which is actually a path for which we don't know this bound. Okay, another question. So as I mentioned, in classical theory, you have ordered, in the classical theory, you have forest with linear, and you have cycles where the extremal function is very far from linear. So we think that the same is true for ordered bipartite graphs. If it's forest, then it's, well, almost linear. If it's not forest, then we know that it's very far from linear. But instead of almost linear, we can ask when it's exactly linear. And so how to characterize those ordered graphs for which the extremal function is exactly linear. So the positive result is an old result of mine with Adam Marcus. That answers another conjecture of the same paper of Füredi and Hajnal, and it says that bipartite matchings have linear extremal functions. So if it's a matching, it's just you have the same number of vertices on the left and the right, and there is a matching between them. But on the negative side, so I also thought that it might be just simple characterization. If the graph contains one of these few subgraphs, then it's not linear, otherwise it is linear, and that is proven to be false by Genezon and Kesseg. The minimal nonlinear patterns, the minimal subgraphs that make the extremal function nonlinear, such that any proper subgraph has a linear extremal function, there are infinitely many of them. So that should not discourage you from thinking that this characterization is possible, because that's also true for the classical theory. The minimal nonlinear graphs in that setting are the cycles. And that's a pretty good characterization, even though there are infinitely many cycles. I really thought that in this case there will be only finitely many examples, but no, there are infinitely many patterns, but the patterns they found have this feeling of like a cycle, so whatever. So just a few words about several forbidden patterns. So if you have, so in this example I just have 2 forbidden graphs. So these are not ordered graphs, just 2 graphs. You look the extremal function. If you forbid both of them, then of course that will be less than just forbidding one of them. So this minimum of the other, if this 2 extremal function, is an upper bound. And something interesting is happening if that the extremal function by forbidding both of them is little o of that. It's not just constant times smaller, but really smaller. And that's a meaningful interaction between the 2 graphs. That means that you can avoid G with this particular graph with many edges, also H with this other graph with many edges. But if you want to avoid both of them, then you will have substantially fewer edges. And we don't know if this exists in the classical theory. Actually, the non-bipartite case, we know that not just little o is impossible, but it's asymptotically the same. So even the constant is 1. That's between them. But it's open in general, and it was conjectured both ways. So for a while, people thought that maybe there is no interaction at all, and now Fodry and Simonovic conjectured the opposite. But for ordered graphs, the situation is different. So you don't have, again, the same thing. ordered version of the Eddington-Shimonovich theorem tells you that this thing does not happen with graphs that are not bipartite. But for bipartite graphs, even the simplest bipartite graphs, passes of length 3, there are lots of interesting interactions with very interesting extremal functions coming up, like n times log n. We take two graphs with each of them have n log n as the extremal function. But if you forbid both of them, it can be linear, it can be n log n, that's when there is no interaction, but it can be n log n over log n. All of these are possible, and there are lots of these interactions that are interesting to study, and it might be also useful. So this is how much I wanted to say about vertex-ordered graphs, and the rest of the talk I will speak about another generalization that is much less developed, and we started to study it more recently, and that's edge-ordered graphs. So you have a graph, simple graph again, and previously you had a linear order on the vertices, now you have a linear order on the edges. So I could draw vertex-ordered graph with the vertices left to right ordered on a line. It's much harder to do it within edge-ordered graphs, so instead I put labels on the edges. So these labels represent the linear order. This edge comes first, this edge comes second, and so forth. And again, if you take a subgraph, then the subgraph inherits the edge ordering. So here is a subgraph. I'm saying here is a, so that's the subgraph. And of course, you are not interested in the labels. It's just the ordering. So this particular cycle of length 4 is the same as that cycle of length 4. It's the same order. It's not a labeled graph. It's just an edge-ordered graph. There is a linear order on the edges. And so Gerbner, Metuku, Nagy, Pálvölgyi, and Wieser are my co-workers on this. So this is very much a work in progress. So first I list a few sporadic results, because sporadic results sometimes are more interesting than the general theory. Here it will be the case that the sporadic results are more interesting, but this is how we started anyway. So these are a few passes of length 3 or 4 that we could figure out the extremal function for. Again, so this is a pass of length 4 with 1, 3, 2 being the ordering of the edges. And so it's linear with the other. There are just two possible orderings here. The other ordering, it's also linear. With the 4-edge pass, it's a bit more interesting. There are versions where you can have the entire complete graph on n vertices without this particular 4-edge pass. So it's n choose 2. This is the highest possible extremal function for any forbidden graph. For others, we know that it's constant times n log n for this particular one, and we actually know the order of magnitude for all of the edge-ordered passes of length 4, except this particular one where we can prove n log n lower bound and an n log squared n upper bound. And I think that this is a problem very similar to finding bipartite ordered forest with high extremal function in the vertex-ordered case. Again, n log n was easy to achieve, and n log n log log n log n is the best known so far. It would be interesting to find a path where the extremal function is bigger than n log n. If it's n log squared, then that would be especially good. And don't be fooled by this one. This has a quadratic extremal function, but that's because of chromatic number reasons that I will speak about later. This is about 4-cycle. This particular 4-cycle we have a lower bound for the extremal function, which is n to the 3/2. That should not surprise anybody, because if you forbid all 4 cycles without caring about the edge ordering, then you get also n to the 3/2. So you have a 4-cycle free graph. You put any edge order on the edges, and that's an example that shows this lower bound. The upper bound is more interesting. That is almost matching here. So it says that basically if you have a 4-cycle in a graph, edge-ordered graph, then right away you will have this specific 4-cycle too. Well, right away meaning a logarithmic error. So what about the general theory? Well, for the general theory, you have to find the right version of the chromatic number for this particular set of graphs. And maybe the first thing that you have to find is the version of bipartite. So in both theories, if the vertex-ordered and the classical, if you have a bipartite graph or ordered bipartite graph, then the extremal function is less than quadratic. And if your graph is not bipartite, then the extremal function is quadratic. And here it is. The same dichotomy happens here. So this is the edge-ordered extremal function, and it's at least n squared over 4 if it's not in the lexicographically ordered bipartite clique. So it's a k and n, and you order both sides of the vertices of the k and n, and then you order the edges lexicographically. So one side matters more, the other side matters less. This is a natural ordering. If your graph is not contained in this, then of course this is an example of a graph avoiding it. Therefore, n squared over 4 is really a lower bound on the extremal function. And if that's not the case, then the extremal function is less than quadratic. It's a power of n that's less than 2. So that's the right analog of bipartite, but what would be the analog of the chromatic number in general? So you need a chromatic number for that, and then you can find the Erdős-Thom-Szymonovich theorem for this particular theory, and it has the same form. So I just put chi prime prime to denote this tricky chromatic number, and it has the same form. The only difference is that I cannot move my slides again, but yeah, this is, well, it's integer, or it can be infinity. So in the case before where the extremal function was n squared over 2, that corresponded to this particular chromatic number being infinity. So you basically have, in that case, you will actually have n squared and choose 2 as the extremal function. So that's a possibility too, but there are no other possibilities. If you divide by n squared, then you get, so these are the only possibilities. And again, for the chromatic number 2, it's not very sharp result, but for any other chromatic number, it is an asymptotically tight. In the remaining 1 minute, I want to say a few words about the Ramsey theory for edge-ordered graphs. These are not very surprising results, that for every k and n, for every k there is an n, such that for every edge-ordered complete bipartite graph with n vertices on both sides, contains a lexicographic version of KK. And this really tells you that there is only one homogeneous order of the complete bipartite graph, and that's the lexicographic order. There is no other homogeneous order, and then you apply Ramsey's theory, and it says that you will find the homogeneous subset, and the homogeneous subset must be therefore this, because this is the only homogeneous order. And there are similar results for, so this was the simplest to state for complete bipartite graph, but there are similar results for complete graphs or complete three-partite, four-partite graph, but all of those have more than one homogeneous order. Not just one, you will have like finitely many, but more than one. This is an absolutely different and for me surprising type of Ramsey result, and it says that for every edge-ordered graph S, there is an edge-ordered graph T, such it will be much bigger, such that for every two coloring of the edges of T, there is a monochromatic subgraph of T that is ordered isomorphic to S. So, of course, you can think that S is like a clique, and T is like a bigger clique, but still it's a very interesting result of Balco and Wieser. And just to give you a feeling about it, this trivially holds for vertex-ordered graphs because there are just one ordering of the clique, but it happens to fail for directed graphs. That's another model of graphs. Instead of edges, you have directed edges, and then it suddenly fails. But for edge-ordered graphs, it is true for some reason. That was my last slide, so thank you very much.
Okay, do we have any questions?
Any idea how much no, let's go back to the previous slide. Oh, I see. No, they took it away.
No slides anymore.
No, let's ask. Please come back to the previous slide. Tech staff, please come back to the previous slide. So what I wanted to ask is whether there is any idea how much bigger this big is from the last slide.
How much?
How much bigger is this? You said that that for every S, there is an edge-ordered graph T that is much bigger. So, how much bigger?
Well, I have to be honest. I was told this is not a published result, and I don't know. I don't know anything about it. I thought about it, and I could verify that it's an interesting result by not being able to prove it myself, but I don't know their proof, anything about their proof.
Okay, any other quick question?
Thank you. Suppose I was interested in this problem, except that I know. Thank you. Suppose I was interested in this problem, but I want to do lattice order on the vertices, or partial order on the vertices. Can I use a lot of your work to go ahead and study that problem?
Sure. Partial. Okay, so the question was what happens if instead of a linear order, you deal with a partial order on the vertices, on the edges. I guess in both cases that's a valid question. So there are two versions of this, when the subgraph have to have all the specified relations between the vertices. So if, but it's okay if the ordering of the subgraph is more specific, then this theory can be embedded in this theory by forbidding all linear extensions of your partial order. But you can also ask, what if you only forbid a partial order where you really insist that in the subgraph, if those two that in your pattern were not comparable should not be comparable, then it becomes trivial, because you can just put a complete graph and you put a full linear order on the vertices or edges, then this will never happen in a subgraph. There is no uncomparable elements.
Okay, perhaps we'll stop it there for now, and any other questions you can ask Gábor in the breaks. Let's thank him, thank Gábor again.